Hi everyone, welcome back. In this particular video, we need to start talking about acid chlorides. Specifically, we're going to first talk about the preparation of these molecules, how these are synthesized, and then we'll look at various reactions of acid chlorides. Now, acid chlorides are the most reactive of carboxylic acid derivatives. So synthetically, they are very useful because they can be easily converted into all of the other carboxylic acid derivatives. So let's look at the synthesis. Carboxylic acid chlorides or acid chlorides are synthesized by reacting the carboxylic acid with thionyl chloride. So when a carboxylic acid reacts with thionyl chloride, you make the acid chloride. Now, it's always good to draw some comparisons or at least make some relations, connections in organic chemistry. So identify that thionyl chloride is the same reagent that we use for converting alcohols into alkyl chlorides. You could convert an alcohol into an alkyl chloride by using thionyl chloride. That's one of the reagents that can be used for converting an alcohol into an alkyl chloride. So let's look at the mechanism of this reaction. How does this reaction work? Now, this reaction involves an initial attack by the acyl oxygen. This double bonded oxygen is called the acyl oxygen. Attack by the acyl oxygen on the sulfur in thionyl chloride. And this attack by the acyl oxygen is assisted by resonance, where the pi bond goes and attacks it. You can draw this same process in over multiple steps by using the lone pair and then engaging the acid oxygen, or you could combine them together in one step like this. And so the double bond there opens up, and this gives us the carboxylic acid with the thionyl chloride attached. So notice the lone pair here became a double bond. So I put a double bond and there's a formal charge on that oxygen. There is a single bond between this acyl oxygen and the acyl carbon now. And this oxygen is now connected to the sulfur, which has a singly bonded oxygen and two chlorines on it. And after the formation of this intermediate, the oxygen here brings its lone pair down to reform to the double bond to the sulfur. And simultaneously, one of the chlorides is kicked out. This brings us to the next intermediate, where we have everything else the way it was. We have the double bonds and everything. The acyl oxygen is connected to S double bond O with a Cl. And plus, we've got Cl minus. The chloride got kicked out. The chloride can then go ahead and pick up that proton or deprotonate to give us R C double bond O, O, S double bond O, Cl plus HCl. And essentially, if you look at it, what we've done here is we've created a very good leaving group. Okay, we've created a good leaving group here. This group is a very nice leaving group, very similar to what happens when we react an alcohol with the thionyl chloride. And so in a subsequent step, after the formation of that, a chloride ion from your reaction mixture, it can come and attack the acyl carbon. And as that attack happens, the double bond opens up here, and it will give you ROCH S double bond O, Cl, with an oxygen with negative charge and a chlorine on it. And from this intermediate, the oxygen collapses back here to reform the double bond. And at this point, there are two leaving groups here. The chloride is a good leaving group, but the sulfur, the chlorosulfonium ion here, that's a better leaving group. So this leaves, and it would give us the acid chloride, which is the organic product that we want. So we make the acid chloride, and plus it's going to give us the sulfur double bond O chlorine with an O minus. This oxygen has 3 lone pairs on it. And this ion can then basically eject chloride to give you sulfur dioxide plus Cl minus. So overall, this is all, or these are all byproducts. You make the acid chloride here. And along with that, you make sulfur dioxide and chloride. So we can add that here. Our other products that are formed here are sulfur dioxide and chloride. Now, sulfur dioxide is a gas, okay? This is a gas. So that's a big advantage to this reaction, because when you do this reaction, you're not generating any major byproducts or side products, because your byproduct is a gas and that just escapes from the system. So you can make the acid chloride very cleanly using this reaction. So that's the synthesis of an acid chloride, by the reaction of a carboxylic acid with thionyl chloride. Next, we're going to look at the reactions of acid chlorides. Now, acid chlorides are the most reactive of all carboxylic acid derivatives. So they react violently with water, which is going to be the first reaction that we're going to consider here. So when carboxylic acid chlorides or acid chlorides react with water, the reaction is generally known as a hydrolysis, very similar to the reaction with water for other functional groups. And what this reaction does is it converts the acid chloride into a carboxylic acid. It converts it back into the carboxylic acid. So we can write an example here as a generalized reaction. So acid chloride, when it reacts with water, it's converted into carboxylic acid plus HCl. That's what happens here. So as an example, let's look at a reaction here. So acid chloride reacts with water to give the carboxylic acid, and plus you've got HCl. Okay. Now the mechanism of this reaction is very simple. It follows the same steps as a nucleophilic acyl substitution. And so essentially the first step in the mechanism is the attack of the nucleophile. Since acid chlorides are very reactive carboxylic acid derivatives, even weak nucleophiles like water, these can attack the carbon, the acyl carbon. And when that happens, it's going to give us the tetrahedral intermediate. Oxygen with negative charge, we've got chlorine, and we've got the water attached here. And once you make the tetrahedral intermediate, the immediate next step that happens is the collapse of the tetrahedral intermediate. The bond comes down. Simultaneously, the leaving group leaves, and so this would give us the protonated carboxylic acid. Plus, there will be Cl minus. And when the Cl minus deprotonates this carboxylic acid, it basically gives us our products. So that's the mechanism of the reaction. An initial attack by the water to give us the tetrahedral intermediate, collapse of the tetrahedral intermediate where the chloride leaves, and then deprotonation to give us the carboxylic acid and water. So this is a very violent reaction, and acid chlorides would just spontaneously react with ambient moisture in the air, and they would slowly decompose to the carboxylic acid. Now, similarly, acid chlorides can react with alcohols, and this reaction, sort of synonymous with the hydrolysis, is called an alcoholysis. Okay, and what this reaction does is it converts the acid chloride to an ester. So you're converting one carboxylic acid derivative into another carboxylic acid derivative. Let's write down a general scheme and then a mechanism for this, very similar to what we did for the hydrolysis reaction. So when acid chloride reacts with alcohol, I'm going to use R prime here. This gives us an ester product. I'm putting an R prime to differentiate the alcohol from the R that was in the carboxylic acid, and plus HCl. So as an example, we can consider the reaction of the acid chloride here with methanol, that's our alcohol, and from this reaction we will get the methyl ester plus you will get HCl. Okay, we can look at a mechanism for this reaction very similar to what we saw with the hydrolysis. The first step is the attack by the alcohol on the acyl carbon. So the nucleophilic attack, which is going to give you a tetrahedral intermediate. The tetrahedral intermediate then collapses. The chloride gets kicked out to give us a protonated ester molecule, an intermediate, protonated ester intermediate, along with the chloride ion. And when the chloride deprotonates this ester, it brings us to the final product, which is the ester plus the HCl. So here's our ester. Okay, this is an ester over here. So it's a mechanism that's very similar to the hydrolysis reaction itself, almost similar. And notice that in these reactions, we are releasing HCl as a byproduct. Since HCl is a strong acid, it always helps to do these reactions in presence of a base, which can basically pick up that acid. So an example of a good base that's used for these reactions, okay, and an organic base that's often used is pyridine. So pyridine is a 6-membered aromatic compound with nitrogen in it. Another organic base that is commonly used is triethylamine. So these are all good examples, or these are both good examples of bases that can be used for this reaction. And what they would do is they would absorb the HCl, absorb in the sense they would react with the HCl, and that way you can avoid any side reactions that would involve maybe another functional group that's present in your molecule. So next is the reaction of acid chlorides with amines. And when we say amines, we can include ammonia, primary amines, or secondary amines. So any of those reagents are included. And this reaction in general is called an called an aminolysis reaction. And what this reaction does is it converts acid chlorides into amides, or this can be viewed as a synthesis of amide from an acid chloride. So let's write down the general equation here. So when an acid chloride reacts with, let's say if we use ammonia as an example, and this reaction is usually done using excess of the amine, so more than one equivalent, at least two equivalents, I would say. This would give us the amide. Now, if we react with ammonia, we just get the primary amide. That would be our product. And plus, along with this, we are going to get ammonium chloride, which would be our side product. Now, if we use a primary amine instead, if we use a primary amine instead of ammonia, again, excess of the primary amine, and we will look at the mechanism, and that will help us understand why we need the excess here. This would give us a secondary amide. Okay, that's an NH. I can fix it here. Say that this is NHR prime. So we get a secondary amide, and along with that, we're going to get an ammonium chloride, but this time it is an alkyl ammonium chloride. So the amine is converted into the ammonium chloride there. So similarly, secondary amines, when they react with acid chlorides, they would give you a tertiary amide as a product. So ammonia gives you a primary amide. Primary amines, they give you secondary amides. So we are reacting with primary amine. And similarly, secondary amines, when they react with acid chlorides, they will give us a tertiary amide. So that's the reaction. Now let's look at the mechanism here. And there we would be able to understand why we need the excess of the amine reagent. Now the mechanism, very similar to what we've seen for the hydrolysis or the alcoholysis reaction. Acid chloride reacts with the ammonia or the amine. So the nucleophilic acyl substitution, the first step is the attack by the nucleophile. This would give us the tetrahedral intermediate. We make the tetrahedral intermediate. The next step should be the collapse of the tetrahedral intermediate. And again, chloride, which is a good leaving group, leaves. And this will give us the protonated amide. We get the protonated amide there. And now, since this is protonated, we need a base to deprotonate it and convert it into the neutral amide. And since amines are good bases, we can just use an excess of the amine. So that's why when we have excess amine, the second molecule of ammonia or the amine can come in and deprotonate that amide to give us a primary amide as a product. And along with that, we will have, there was chloride here. So along with that, overall, we are going to get ammonium and chloride. And so now if you're doing the same mechanism with a primary amine, you just replace the ammonia with a primary amine here, replace the ammonia with primary amine there, and you're looking at the mechanism for the reaction of an acid chloride with a primary amine to convert into a secondary amide. Now, let's look at some examples quick here so that this makes sense. And we will just put down some specific examples here. So let's say we have a cyclohexyl or a benzoyl chloride, let's say. If you react the benzoyl chloride with excess ammonia, this is going to give us benzamide. Okay, it would give us benzamide. The Cl is replaced by NH2, and plus we will get ammonium chloride as our side product or the byproduct that's formed. If we have, let's say, 1, 2, 3, 4, so that's a butanoyl chloride. React this with methylamine, let's say. Now we are using a primary amine, so our product should be a secondary amide. So the product that we're going to get is going to be NH with a CH3 and plus, okay. And this is in excess, so we will get CH3, NH2 plus, Cl minus. That would be the side product. And so similarly, if we have a secondary amine as our reactant, then our product is going to be a tertiary amide. Okay, so that's the reaction of acid chlorides with amines. It gives amides as product. Next, we're going to consider the reduction of acid chlorides. This is the reaction of acid chlorides with hydride-based reagents like lithium aluminum hydride. And we'll also learn a new reagent over here. Now, what these reactions do, the reduction reactions do, is they convert the acid chloride into an alcohol or an aldehyde, depending on the choice of the reagent. So the reagent here is very important. Now, the overall reaction or the net reaction essentially is the acid chloride reacting with lithium aluminum hydride. Sodium borohydride would not work well here. So lithium aluminum hydride in excess. Okay, and we'll talk about why do we need the excess and what would happen if we don't use an excess. So lithium aluminum hydride excess followed by a workup acidification to give you the primary alcohol. Now, essentially notice that what happens is the acyl carbon is converted into the alpha carbon in your alcohol molecule. As an example, benzoyl chloride reacts with excess lithium aluminum hydride followed by an acidic workup to give you benzyl alcohol. The acyl carbon is converted into the alpha carbon in the alcohol. Let's look at the mechanism of this reaction, and then we can start talking about why do we need an excess, what would happen if we don't have an excess, and how does the acid chloride convert into the alcohol here. And important thing to note here, the alcohol is a primary alcohol. You will not get a secondary alcohol here. That would not be possible because you're using an acid chloride. You cannot make a secondary alcohol here. So the alcohol is always going to be a primary alcohol product. So like all other nucleophilic acyl substitution reactions, the mechanism starts with an initial attack by the nucleophile on the acyl carbon. And the nucleophile, in case of hydride reagents, is the hydride. So from a reagent like lithium aluminum hydride, one of the hydrides can come and attack the acyl carbon. Simultaneously, the double bond opens up, electrons are pushed to the oxygen atom. And this would bring us to our tetrahedral intermediate. So very standard among all of these reactions that we're looking at. So you get that, and plus they should have ALH3. So you get this intermediate, and since you make this tetrahedral intermediate, the next step is the collapse of the tetrahedral intermediate. The chlorine gets kicked out. A hydride is a bad leaving group, so the hydride would not be getting kicked out here. So the chloride is the better leaving group here. That would get kicked out. And notice what we get. We're going to make an aldehyde. Okay, so the acid chloride is converted into an aldehyde. But as we know from our prior experience, lithium aluminum hydride would also react with the aldehyde. So the reaction doesn't really stop here, or in fact, it is not a wise idea to actually try stop at the aldehyde stage. So essentially, we use excess lithium aluminum hydride, and what we do is the aldehyde now reacts with another molecule of lithium aluminum hydride. In fact, I want to point out that a molecule of lithium aluminum hydride, in fact, has 4 hydrides on it, and all of them can be used in principle, okay? But for the mechanism here, we're going to use another lithium aluminum hydride. So another hydride goes and attacks the carbonyl carbon now. We started with an acyl carbon because it was a carboxylic acid derivative, but now it's an aldehyde, which is a carbonyl compound. So this is now a carbonyl carbon. The hydride attacks the carbonyl carbon, the double bond opens up. And so essentially what we get here is O minus with 2 hydrogens on it. And plus we will have the ALH3. Okay. And so what we've made here is an alkoxide. Now at this point, further reduction is not possible. And so when we do the second step, which is the hydration step, so all of this is happening in the first step, and now we get to the second step. And so the alkoxide gets protonated during the acidic workup, and that gives us the primary alcohol, plus there's water. So that's how we make the primary alcohol. And as I mentioned, since lithium aluminum hydride is a highly reactive hydridic reagent, it does not make sense to actually try and stop at the aldehyde stage. In fact, if you try that, what's going to happen is you're going to get a mixture of products, because you might be able to stop at some aldehyde, but some aldehyde is going to get reduced to the alcohol. So you will have like multiple products there. So it is wise, it is better to actually use excess lithium aluminum hydride to convert the acid chloride all the way to the primary alcohol. So that's the mechanism. 2 attacks by the hydride on that carbon. First an acyl carbon and then a carbonyl carbon. Next, we're going to look at a reagent that is specific for converting the acid chloride into an aldehyde. It would let us isolate the aldehyde, but it is not lithium aluminum hydride. So a new class of reagents that we're going to introduce here are the lithium trialkoxy aluminum hydrides. These reagents look very similar to the aluminum hydride, lithium aluminum hydride, except for the fact that 3 of the 4 hydrides have been replaced by the alkoxy group. So this change tunes the reactivity of the hydride. It makes it a little bit more specific, and it is less reactive compared to the lithium aluminum hydride itself. And so what we're able to achieve by that change is the selective conversion of an acid chloride to an aldehyde. So the addition of these alkoxy groups, what it does is it maintains the reactivity of the aluminum hydride towards the acid chloride. But the aluminum hydride reacts much slower with the aldehyde. So that allows us to actually isolate the aldehyde. And so we can convert the acid chloride into an aldehyde. So an example for this reagent is the lithium tri-third butoxy aluminum hydride, where these alkoxy groups are third butoxy groups, and there's one hydride reagent. Now, the overall scheme of the reaction looks very similar to the use of the aluminum hydride. We don't need to use excess reagent here, But when the acid chloride is reacted with the lithium tritert butoxy aluminum hydride, followed with an aqueous workup, you get the aldehyde as the product. Now, again, I want to mention the tritert butoxy aluminum hydride, it still reacts with the aldehyde, but the reaction is much slower. So that allows us to actually isolate the product. As an example, when you use this butanoyl chloride and you reduce it with the lithium tritert butoxy aluminum hydride, the product is going to be butanal. So we get the aldehyde here. Now, the mechanism of this reaction is very similar to the reaction of the acid chloride with lithium aluminum hydride, except for the fact that you can stop at the aldehyde stage. The lithium tritert butoxy aluminum hydride, you do not have to show further reaction with the aldehyde that takes you to the alcohol. Next, we're going to talk about the reaction of acid chlorides with organometallic reagents. Now, these are reagents where there is an organic part that is bonded with a metal part. A classic example being the Grignard reagent. But in this particular section, we're going to talk about the reaction of acid chlorides with Grignard reagents, as well as Gilman reagents that are copper-based reagents. Now, when an acid chloride reacts with a Grignard reagent, a general scheme for the reaction involves excess Grignard reagent. Again, we will talk about this when we get to the mechanism, but when an acid chloride reacts with an excess of a Grignard reagent followed by an acidic workup, you get a tertiary alcohol as your product. So for example, when this cyclohexyl carbonyl chloride reacts with ethyl magnesium bromide in excess followed by an acidic workup, it gives us the tertiary alcohol that's shown. Let's look at the mechanism of this reaction as to how we end up with the tertiary alcohol and why do we need the excess of the Grignard reagent. So the mechanism of this reaction, like all other nucleophilic substitution reactions, start with the attack of the nucleophile or attack by the nucleophile on the acyl carbon. So if I have my acyl chloride, in the first step, the Grignard reagent is going to attack the acyl carbon, and the double bond is going to get pushed up. And this would bring us to a tetrahedral intermediate. So R prime, we've got O minus Cl. Now from this intermediate, again, like all nucleophilic substitutions under nucleophilic or basic conditions, the tetrahedral intermediate collapses and the chloride gets kicked out. So this will bring us to now a ketone. So notice how the acid chloride is converted into a ketone. And as we know, Grignard reagents, they attack or they react very favorably with ketones, carbonyl compounds, whether they're aldehydes or ketones. So essentially what happens at this point is the reaction does not stop here. The ketone that's formed reacts with another equivalent of the Grignard. So this is a nucleophilic acyl substitution, and then we are doing a nucleophilic addition so that we get the alkoxide minus, we've got R, and we have the MgBr over here. And so that's all happening in the first step. So starting from here, this is all the first step going on. And in the second step, when we do the acid workup, or when we quench this reaction, then the alkoxide gets protonated to give us a tertiary alcohol plus the magnesium species, which most likely is MgBr with a hydroxyl to it. But the key is that we make the tertiary alcohol, which is our organic compound. So very similar to the reaction of acid chloride with lithium aluminum hydride, which we went over a little bit ago. The key here is that when the Grignard reacts with the acid chloride, it generates a ketone intermediate. And we are unable to isolate this ketone because the Grignard is also highly reactive towards the ketone. So the reaction keeps going and we get the tertiary alcohol. And it does not make sense to actually stop it at the ketone, because if we try that, you're probably going to end up with a mixture of products. So that's why we use the excess Grignard reagent in this reaction. Now, in a case where we want to go from an acid chloride to a ketone and stop there, we have a different reagent, which is the Gilman reagent. Gilman reagents are represented by the general formula of R2CuLi. So there are two alkyl groups or carbon-containing groups that are connected to a copper. This is the connectivity. And these are commonly referred to as lithium dialkyl cuprates. Okay, that's this molecule. So as an example, you can see that an example may be Me2Culi. So two methyl groups on a copper, which is negatively charged with the lithium. So that would be an example of a Gilman reagent. Now, Gilman reagents are more selective than the Grignard reagents. And the reason this is because when you compare the structure of the Gilman reagent to a Grignard reagent, the carbon-copper bond, because realize that this R group is a carbon-containing group. So the bond between the copper and the carbon here in a Gilman reagent is less polarized than the bond between carbon and magnesium in the Grignard reagent. Now, less polarized means there is less charge separation in some sense, okay? And that's because the copper is less it is a less electropositive metal than the magnesium. Magnesium is a highly electropositive metal. And so that results in this lower polarization of the bond. And because of that, and hence what happens is the carbon in a Gilman reagent, so this R group, or the carbon that's connected to the copper in a Gilman reagent, is less nucleophilic overall. So it's not as strong of a nucleophile as a Grignard reagent is. And that's because of the greater polarization that exists in a Grignard reagent between the carbon and the magnesium here. So as an example for the Gilman reagent, we can write, say, benzoyl chloride reacts with dimethyl or lithium dimethyl cuprate, okay, lithium dimethyl cuprate. And when you follow this up with a workup, you can make a ketone where one of these methyl groups, not both of them, one of these methyl groups has added to the acyl carbon. So our product is a ketone. So whatever R group is in the Gilman reagent, one of those substitutes the chloride here. And the mechanism here again is very similar to the mechanism of the reaction between an acid chloride and a Grignard reagent, except that you would not go beyond the ketone product. Now, one advantage to the Gilman reagents as compared to the Grignard reagents is that, notice in a Gilman reagent, you can add an organic group and stop at the ketone, which means Once you have this ketone, now you can add another Grignard reagent. So if I add a Grignard reagent to it, and follow it up with an acidic workup, it will give me a tertiary alcohol. It will give us a tertiary alcohol where I can have two different R groups, because this R in the Grignard reagent does not have to be the same R that was there in the Gilman reagent. So you can actually make a tertiary alcohol with different R groups added. Now, clearly you cannot do this using a Grignard reagent, because when you look at a Grignard reagent, if you react the benzoyl chloride with a Grignard reagent, and you do this in excess. So let's say if I'm using some RMgBr, I'm using an excess of this followed by an acidic workup, my product is going to be a tertiary alcohol, but both of these R groups are going to be identical. But the sequential use of a Gilman followed by a Grignard allows me to bring in two different R groups as far as organic synthesis is concerned. So that's one advantage of the Gilman reagent. So that brings us to the end of this video, where we've looked at several reactions involving acid chlorides. We initially looked at the synthesis of acid chlorides, and then we've looked at various reactions that use acid chlorides as a starting material. And several of these reactions, notice, converted the acid chloride into another carboxylic acid derivative. And because acid chlorides are the most reactive of the carboxylic acid derivatives, that makes it a very practical reagent to use, because you can make any other carboxylic acid derivative from an acid chloride. I hope all of you find this video useful. Bye.